have Jacopo here, Jacopo Bassi, who is giving his third lecture on the boundary content of the left and right action, the case of SL2Z and SL3Z. So,
thanks. So first of all, I want to apologize in advance because the coffee machine is broken and this will have some consequences on this lecture. So, by the way,
broke it?
No, it's always like this. Like when I was here, it was like 2 or 3 times per week. It was broken. But we cannot complain. It's for free. So it's so last time I just sketched. I just defined these parabolic subgroups associated to catopods and the associated homogeneous spaces for SLDR. Now, what I want to do in this lecture is so we saw that SL2Z is biexact and derived some interesting consequences of this. We want to see what happens if we take something larger. And first of all, I will try to see what happens for the semi-direct product of SL2Z acting on Z2. And then we will move to SL3Z and see what we can say about the structure of the von Neumann algebra, in particular this solidity result, and the regularity of the Calkin representation associated to the left-right action. So first of all, okay, so I will use the following notation, that if I take an element gamma, let's say in SLDR, I denote by lambda 1 of gamma greater or equal lambda 2 of gamma, and so on, the singular values. So they are just the if you want, if you write gamma in the KAK decomposition, these are the diagonal entries of this matrix, and I always suppose that they are arranged such that the first one is the biggest and they are decreasing. So okay, I want to start with the lemma that you cannot find in the literature. Usually, it's very hard to I couldn't find it. There is some hint in the paper in the book by Zimmer on semi-simple groups, but the lemma is the following: that suppose we have gamma n going to infinity in SLDR, and suppose that there exists a k-tuple such that of this form, such that lambda ki plus 1, I will denote just n to mean lambda of gamma n, over lambda ki goes to 0. Then, up to taking a subsequence, so I will always use the following. If you have this homogeneous space, I will denote by mu k the probability measure on this, that is given just by pushing forward the k invariant probability measure on the quotient by the Borel subgroup, on the minimal parabola. So this is the push forward. K invariant on x 1, 2, 3. But actually, it's not. I mean, you can take any diffuse measure usually, but we will fix this. So up to taking a subsequence, what happens is that
what is x?
this is I defined it here. So the k-tuple is 1, 2, 3. So the parabolic subgroup is the minimal parabolic.
Yeah, okay.
Yeah, this is what I mean. And then you take there the k invariant probability.
On xk.
Yes, it's the measure I fix.
Which is k-invariant.
Yeah, yeah, but actually we will need just diffuseness. But I choose this. Maybe if I...
The G quasi-invariant measure.
Yes, exactly. So after the case subsequence, what happens is that if we look at the... so for every... there exists X in this homogeneous space given by the decay tuple is the one appearing here, such that for mu k almost every y, the limit is this X. Okay. So how do we prove it? We prove it in the following way. So let A inside SLDR be given by the matrices such that for every I from 1 to L, the ith, I think it's called the principal minor, is inverted. So this is the following. You take G. So we are saying that the 1-1 entry is different from 0. Take this 2x2 matrix. This is invertible. You take this 3x3 matrix. This is invertible, and so on. Okay, so we fix this. Now it's clear that A is open dense because the complement is defined by zeros of polynomials. And okay, now there is the following fact that is basically Gaussian reduction. That whenever you take G, you can write it as a product P times B, where P belongs to the subgroup given by the lower triangular matrices with 1 on the diagonal and something here. And B is in the Borel, so it's the upper triangular matrices, but with some coefficients also on the diagonal. Why is this true? Because you see, we start, so we have this G11, G12, G21, G22, and so on. Now we multiply on the left by a matrix like this, 1, 1, 0. Now here I put minus G21 over G11, and I keep all zeros elsewhere. Is this okay? Yes. So what we obtain after this is a matrix in which I don't do anything on the first row. So it's G11, G12, and so on. Now I have a 0, and I modified this row. So it's G22 prime. And now I have something here, and so on. Okay. So now I go on, and for example, I take, I multiply this by something like 1, 1, 0, minus G31 over G11. And then in this way, I get rid of all these entries. And so I end up with something like G11, G12, all zeros here. And now I modified all this. But now I can go on. For example, I want to get rid of this. How do I do it? Well, you see, I have to multiply by, what is it? It's minus, and now the coffee, G3 prime over G22 prime. And the reason why I can do this is that the effect here of doing this was to multiply this block by an invertible matrix. And so this should be different from 0. And so it's clear now that I can go on. And at the end I obtain something like this. Okay, but then now I multiply on the right by some element. I write G, so G is equal to PB. I multiply by Bn in such a way that now I obtain P, that is this lower triangular matrix, times something that is of the following form. 1 over lambda 1n, 1 over lambda dn, and all zeros. Okay? Now what I do is, so what is this multiplication? This is something like this, right? It's we have 1 over lambda 1n. Here we have something over lambda 1n, and so on. On the second column, I have 1 over lambda 2n, something over lambda 2n, and so on. So you see that these eigenvalues appear on the columns now. So now I multiply on the left by this matrix, the singular values, lambda 1n, lambda 2n, and so on. PBBN. So what is the effect of this? You see, now I have to write this in blocks. So you have this block is K1 times K1. Here I have a block that is K2 minus 1 times K2 minus K1 here, and so on. Now I do this multiplication, and what is the effect? Well, I will have here all ones, and here, now what do I have? For example, if I take something on this entry, I will have something times, now I have a lambda K1 plus 1 over lambda 1. Here I have something times lambda K1 plus 1 over lambda K1, and so on. So what I obtain at the end is a matrix in which for every n, oh, this is n, of course. It's a matrix such that for every n, these are all the entries are uniformly bounded, and you see, if I have something here that goes to 0, then every element on this column will go to 0, because here I'm just taking lambda. So if I go below, I have something smaller than this, because this is how I define the order on the singular values. And so, but here, for example, this goes to 0, so all of this will go to 0, and so on. So from this choice that I erased, from the fact that lambda ki plus 1 over lambda ki goes to 0, we obtain that up to a subsequence, this will land inside this parabolic circle. But then it's clear, because now so now what we saw is that this matrix lambda n applied to G, okay, this will go to this particular point, and so it's from this it's not difficult to see that then so our matrix gamma n is something like Kn lambda n Kn prime. So up to taking another subsequence, Kn goes to a certain k, Kn prime goes to k prime. And so if I do this here, we have that k minus 1, gamma n, k prime minus 1, applied to G, pk, this goes to this point, and so I put k here, and the claim is proved. Because, so we saw that for all the elements of this form, we just took G in this particular A, and this is enough. Okay, so we saw that we have this sort of proximality, right? For example, okay, now I want to briefly spend some words on this work by Boutonnet, Johanna, and Peterson, but just because we want to address the problem with Z2 cross SL2Z. So they define the following. So this is Boutonnet, Johanna, Peterson. They say the following definition. Suppose we have an action of gamma on X, compact Hausdorff, and we have mu, a probability measure on X that is quasi-invariant. Now they define the following object. It's called the boundary piece. Is denoted by delta mu gamma. Now it's quasi-invariant. I suppose this is not invariant. So in this way, I define this object to be the set of free ultrafilters, such that if you take the limit for gamma that goes to omega of what? Of gamma mu minus gamma h mu, this is 0 for every h in the group. So now, since I assume that the measure is not invariant, this is actually a subset of the Stone-Check boundary. And okay, so for example, if I take the real projective line, I take this this measure mu, that is in this case mu of 1, 2. So in this case, if you take SL2Z acting here, the boundary piece of SL2Z is everything. So, and this actually follows easily from this lemma. Because now if you have, so the point is the following. Example, so the proof of the example. So, what is we take the following two measures. So, take omega in delta beta SL2Z. And now I have two measures that I want to compare. One is limit gamma that goes to omega of gamma mu, and the other is limit of gamma that goes to mu of gamma h mu. So you see, here is the probability measure on RP1. We have these 2 points, mu prime. So as we saw in the first lecture, whenever you have the range that is a second countable space, you can qualify sequences. And in this case, so we see really at the definition of these maps. So it means that for every open set around one point, and for every open set around this other point, the inverse image is an element of the ultrafilter. So this is a set in omega. This is also a set in omega, and they should intersect. So I can take something here. And in this way, we obtain a sequence gamma n. So we find gamma n such that nu is the limit over n of gamma n nu, and nu prime is the limit on n of gamma n h mu. Okay, but then we are done, because up to taking a subsequence, the limits are the same, and in this particular case, if you have a divergent sequence, it's automatic that lambda 1 over lambda 2 of n goes to 0. Lambda 2 over lambda 1 goes to 0. Because the sequence is diverging. And so in this case, we can apply the above lemma, so by the lemma, up to subsequence. Up to subsequence, we have that for almost there exists a point x in the real projective line, such that for mu almost every y in the real projective line, the limit in n of gamma n y is equal to x. But then it's just an application of Lebesgue-dominated convergence theorem to see that then this measure will go to the delta on this particular point, and also this. And so we saw that actually every free ultrafilter is in the boundary piece associated to this data. Okay. Now, what can we do? Now we go to SL2Z cross Z2. And now we will almost prove by exactness. There is just one thing that we don't prove, but so what is the idea? So let's say proposition Z2 cross SL2Z is by X. Almost. So here we do the following. Consider the map, call it pi, from so call this group gamma. The map goes from gamma to SL2Z, and this is just the projection on this factor. And we consider, we divide, so we write delta beta, the free ultrafilters on gamma, as the union of two sets, x1 and x2. x1 is defined as the inverse image under the extension of pi to the Stonechek compactification of the Stonechek boundary of SL2Z, intersection with the Stonechek boundary of gamma, and x2 is what's left. It's pi beta to the minus 1 of SL2Z, intersection with the Stonechek boundary. Okay. So now, what we have, now you see, if you take a free ultrafilter here, we saw, I just erased it, we saw that every point here is in the boundary piece associated to the action on the real projective line. So in particular, every point in this, I mean, the action of SL2Z on the real projective line comes, if you want, from the action of gamma on the real projective line, because you Gaussian by the normal subgroup, that is Z2. So we have gamma acting on the real projective line, and okay, now this action is amenable as well. Because we are quotienting by an amenable subgroup.
And x1 is contained in the boundary piece associated to this, to mu on a real projective line of gamma. Now there is a fact that I want to, so lemma. Suppose that you have this action of gamma that, and you have this mu that is quasi-invariant, not invariant. And suppose that if the action of gamma on x is amenable, then we construct the boundary piece, and we see that the action of gamma on this particular space, that is the spectrum of the continuous functions on the boundary piece, which are fixed by the right action. I read it like this. This is amenable as well. Let me sketch the proof. So the proof is really the following. So I think you told about Poisson maps, or no? Okay, we define this map. We take pi mu from C of x to L infinity of gamma, and pi mu is just given by the following. You take f, and you send it. I want to tell you what is p mu of f, so I have to evaluate on gamma, and this is gamma mu of f.
So Jacopo, what is gamma acting on sigma? I missed it. So what is that?
Sigma is the spectrum, the characters on this algebra.
Okay.
Yeah, this topological
Continuous
space.
functions on that.
Fixed by the right action.
Fixed by that.
I didn't, yes, thanks. I didn't say this, that if you take a boundary piece associated to an action, this is closed, and this gamma times gamma invariant. It's invariant both for the left and the right action. So we can consider this algebra. Now, I take this particular map, and this is a gamma equivariant UCP map.
I mean, Hannah defined this.
Ah, sorry. I forgot, sorry. Thanks. Yeah, this, you see the coffee is important. So, okay, we have this. And now what I want to say is the following, that now I compose this map with the map, I call it phi, that is just the restriction. So phi from L infinity of gamma to continuous functions on delta mu gamma is just the restriction. So here we have this closed set inside the Stone-Check compactification, that is delta mu gamma, and restrict functions. So the claim is that phi composition pi mu, the range of this is inside this algebra, the fixed points for the right action. Why is this true? Well, we just have to check the following, right? That if you take, so we write explicitly this map. So we take omega in delta mu gamma, and we want to check that, so we take f in C of x, that the limit for gamma that goes to omega of p mu of f, this is a certain value, is equal to the limit for gamma which goes to gamma h of p mu of f, to omega h for any h in gamma. Okay, but so why is this true? So what is this? So you see here we are taking a map from gamma to plus norm of f minus norm of f. Suppose the limit is this point. We are saying that for every open set, the inverse image is an element, so it's A belongs to this particular ultrafilter that is omega h, but it follows basically from the definition that this is if and only if A h to the minus 1 belongs to omega. This is because it's very easy to see what is the extension of the action on the ultrafilters, and it's just given by this formula. But so this means that, you see, if we are considering this map, now I consider another map that is the map from gamma to gamma, that is multiplication on the right by h. What we are saying is that this limit is equal to the limit of something else, that is, so this is equal to the limit for gamma which goes to omega of this other map. P mu of f, this is in gamma h. This was just to say this. Okay, but then it's done, because I don't want to erase that. Here. Because now we just have to check, well, what is this? The limit for gamma which goes to omega of absolute value pi mu of f in gamma minus pi mu of f in gamma h, and this is equal to the limit by definition of gamma mu of f minus gamma h mu of f. And now this is 0 because we picked omega in the boundary piece. So we just checked that whenever I do this composition, pi mu of f with the evaluation on the boundary piece, and I translate the point in the boundary piece, the functions I obtain have the same value. So I checked exactly that it lands in the functions that are invariant under the right action. And so now it's a general fact that, so we have this from psi of x to this gamma equivariant UCP, and from this I can define a continuous map. So a continuous map from the spectrum of this to probability measures on x, that is gamma equivariant and continuous, and this is just given by, I take y and I send it to, so this is called this, I don't know, capital phi. I send it to a capital phi evaluated on something in y. This is the map.
The dual map, right?
Yes, exactly. It's exactly the dual map. So now, if the action of gamma on x is amenable, Ixon, observe that also the action of gamma on the probability measures on x is amenable, and so we are done. Okay, this was this lemma. So in this particular case, we apply this lemma, and we see that so the action of gamma on continuous functions on delta mu at P1 gamma is amenable. And that x1 is contained here. This is what.
Is that phi up there, isn't that equivariant already?
It's gamma equivariant, yes.
So did I miss any, so am I missing, because then you get already a map from the spectrum of that to Stonecheck compactification, which you know already is amenable. So that's a general fact if you, I mean, that we, right, into, because gamma on x is amenable, gamma on Stonecheck is amenable.
No, but I mean, if you look only at this,
Yes.
you don't let inside, the image is not the one that are invariant under the right action.
Ah, so you, okay.
Yes, this is what I want.
Give me that map. Okay.
Yes, yeah, otherwise, of course. Yes. I mean, if you restrict an amenable action to a closed gamma invariant subset, it's amenable. Yeah. Yeah, thanks. So, So we have this, and so the important point is that this is contained in something, in a bigger space on which this is true. Now let's see what happens for the other part. We have x2. I mean, the left action on every boundary piece is always a minimum. Oh yes, this is true. So the other part, you see, this is okay. It's not difficult to see. What is this? What is this set? These are ultrafilters. So omega in x2 is actually of the following form. Is of the form omega equals g times omega prime, where omega prime is a free ultrafilter on Z2. And this is something that it's not difficult to see. But so we look at this. Now, we see the following. So suppose we have G in this copy of Z2 that is given by the following. 1, 1, 0, 0, 0, 0, and here I have V1, V2, 1. So I look now at the singular values of this. So I take really the definition. I take G transpose G. What is this? It's 1, 1, 0, 0, 1, 2, times 1, 1, 0, 0. So this is 1, 1, 0, 0, V1, V2, V1, V2, V1 squared plus V2 squared plus 1. So in particular, if I take now G transpose G minus the identity, three-dimensional identity, this will be 0, 0, 0, 0, V1, V2, V1, V2, and something else here. Oh, but then this is rank at most 2. The determinant of this is 0. So 1 is an eigenvalues of this, so it's an eigenvalues also of the square root of this. And so every element here has a singular value that is 1. And this exactly implies that if you take a limit there, a sequence there, we are in the position in which, so if gamma n goes to infinity in Z2, then when you write gamma n, the singular values, the matrix of the singular values is something like this. You have lambda 1 n strictly greater than lambda 2 n, strictly greater than lambda 3. And so for what we said before, this means that if you look at SL3R over the Borel subgroup, you have this, every sequence will contract everything, almost everything to a point. This is exactly what we saw before. But of course, this is an amenable action. What is that? So we have that this other space X2 is contained in the boundary piece associated to mu, what is 1, 2, 3 of this copy of Z2. Okay. And now what we have? Okay, we have amenability of the action here. So from what we said before, here we have the continuous functions delta mu 1, 2, 3. No, of gamma, yes. So X2 is actually contained. I tell you that it's contained. So every free ultrafilter, yes, every free ultrafilter. So you see, X2 is contained there, because every free ultrafilter there is such that it has this property, and so in particular, yeah, from what we saw, it satisfies the assumption. It's contained actually. It's made of ultrafilters like this. So it's basically based on sequences, as we saw before, that contract everything to a point. It's exactly the argument that we said before. Now, the action of gamma on the associated space, the Gaussian by the Borel subgroup, is amenable, and so the action of this on gamma right is amenable. Okay, but then we are in the following position. We have, this is delta beta gamma, we have these two closed subset. One is delta mu on the real projective line of gamma, and we have another closed subset that is delta mu of this other Borel subgroup, that is the three-dimensional one of gamma. Both actions, when we see them on the fixed point for direct actions, are amenable. And now there is a procedure that, this is the part I will skip, that is called patching by exactness. That is the following, that if you have such a situation, you have a finite number of boundary pieces with this property, then what you actually obtain, you can glue them in a certain sense. And what you obtain is that the action of gamma on all the Stonecheck compactification, the part of the Stonecheck boundary that is fixed by the right action is amenable. And this is enough to obtain by exactness, because if you want, you can do the following. You take the extension of the inverse map at the level of the Stonecheck boundary, and this gives an isomorphism between this algebra and the algebra of left invariant function. And you do it, you have this splitting phenomenon, the one that we already saw before. And so basically you can take this from delta beta gamma to the product, the spectrum of functions which are fixed on the right, times functions, spectrum of functions which are fixed on the left. And you have the left action only takes place here, the right action only takes place here, and here you have amenability, and so you have amenability also on the Stonecheck boundary. Okay, this was just to say what happens for this particular group, and the proof really is something very, very peculiar of this group. So now let's see. At the end we wanted to see what happens for SL3Z, and so we took a group in between. We saw that this group is actually biexact. So let's pass to SL3Z. So now I will use. What we want to see is the following. From now on, gamma is SL3Z, and we want to check two properties. So we want to understand how far, let's say, how far is the von Neumann algebra from being solid, and we want to understand the regularity properties of the Calchi representation associated to the left right action. Okay, so we start with this, and here we just use basically an application of the ideas that Mehrdad told us yesterday.
If you want to make a break, I mean, it's maybe a good point.
Okay.
Yeah,
Yeah, I mean it's up to the audience. Yeah.
we can have 5 minutes.
Thank you, Bashir.
No,
I mean, we are kind of used here.
it was a good point. I mean, just you, before starting something new, I mean, not completely.
Yeah, you're right. You're right. You're right. Welcome back. So, what I want to say is that, so let gamma, this is a general fact, acting on X, compact Hausdorff, mu, the probability measure on X, and let gamma n be a sequence in gamma, such that there exists X in X, satisfying gamma n y goes to X with mu almost every point. Then, if you look at the commutant of gamma n inside L gamma, this is contained in the von Neumann algebra of the stabilizer of this point. And this is actually really the ideas that Merdad told us yesterday. So how do we prove it? First of all, observe the following lemma. So under these assumptions, there exists a state psi on BL2 gamma such that psi restricted to L gamma is equal to the trace, psi restricted to pi mu of C of X, where pi mu is the map that I used above, is equal to the delta on this point, and also that psi, when you compute psi A p mu of F B, this is equal to psi of p mu of F A B for every F continuous function on X, every A in the commutant, and every B in B of H. So basically the point, I will not give the details of the proof, but the point is that if you take the joint action of this lambda gamma n, this sequence, lambda gamma n, p mu of f, lambda gamma n star, this will go strongly to the delta x times 1. And so we can consider tau composition at un, take a limit, a cluster point of this. This will be the state psi, and basically this is what I want. So the important fact is that gamma n, lambda gamma n, p mu of f, lambda gamma n star converge strongly to delta x. So in particular, this you see this state we obtain, these elements are in the multiplicative domain. So now let's see from the lemma how we prove the proposition. So fix this state psi, let psi as above. Now what we want to see is that whenever you take a unitary in this von Neumann algebra, in the commutant of, this is lambda gamma n, un is lambda gamma, lambda. Whenever we take a unitary in this algebra, we want to check that the true norm of the expectation on L of gamma x of u is 1. This is what we want to check. Okay. So, how do we see it? So, first of all, we approximate U star by U0. So, pick epsilon. We approximate this by U0, where U0 is in the group algebra. And we write it in the following form. Sum S in a certain finite set, in gamma, F intersection gamma x, alpha S, lambda S, plus sum S that is outside the stabilizer. Now, we compute. You see the absolute value of psi of p mu of f times u0 minus 1. This is less or equal to, so this is in the multiplicative domain, so it's in general is less or equal than f of x star f of x square root times the 2 norm. So if we now choose f such that f of x is 1, exactly what like that. F of x is 1 and f of sx is equal to 0 for every s that is outside the stabilizer. So if we choose f in this way, this is 1. And so this is less or equal than the norm of u star minus u0, and this is less than epsilon. Okay, so this is the first computation. Now we compute psi of u p mu of f u0. So this by the lemma equals psi of p mu f u0, and so this is greater or equal than what? Then absolute value of psi of p mu of f, that is just f of x, minus absolute value psi p mu of f u0 minus 1, and this is, for what we saw, is greater or equal than 1 minus epsilon. Okay, this is the first computation that we need. But now we have also the following, that the absolute value of psi of u p mu of f u0 is less or equal than, so we write u0 as the sum. So this will be less or equal than psi of u p mu of f times the expectation on the stabilizer, lambda s, plus absolute value of psi u p mu of f, the expectation on the complement. So now, well, what we can say about this part? Now, for every of these elements appearing in the sum, you see, if I take absolute value of psi u p mu of f lambda s, now I multiply here by lambda s minus 1, so I put lambda s minus 1, and so you see, here I have absolute value of psi u p mu of f, u lambda s minus 1, p mu of f lambda s. Now this is just p mu of F composition S, hopefully. And this is in the commutative domain, and so this is 0. So all these terms are 0. Because we assume that F vanishes on the translated by S. And so at the end we only have this contribution. And so what we saw is that, but this contribution, where I should, this contribution then is less or equal than what? Then the true norm, so it's this one, is less or equal than the true norm of the expectation on L gamma x of u, which is, if you want, less or equal, so is u0, less or equal than the expectation on L gamma x of u plus epsilon. And so we are done, because this was greater or equal than 1 minus epsilon, but it's also lesser or equal than 1 plus epsilon. Okay, so at the end we saw this. And now we have to apply it. So we take SL3Z. So what is the point of taking SL3Z? It's an algebraic result. So it's let's say lemma. This was proved by Osawa, but I think it was known that if gamma n goes to infinity in SL3Z, then so the result is really this. If lambda in SL3Z is an infinite subgroup, then there exists an element in this subgroup such that the singular values are all distinct. Okay? Okay, but then as a corollary of the proposition, we obtain the result, because we know that if the eigenvalues are all distinct, then when you take the action on the Borel subgroup, you have this infinite sequence that makes everything converge to a point, almost everything. So we can apply the proposition. And so what we obtain as a corollary is that if lambda in SL3Z is an infinite subgroup, then we can find this sequence in lambda, and so there exists x in SL3R over the minimal parabolic, such that the commutant of L of lambda inside L of SL3Z is contained in the stabilizer of this point, in L of the fixed point X intersection SL3Z. So in particular, what we saw is that if you restrict at least to group algebras, yeah, it's a huge restriction, but this is all we can see by now. It's if you restrict to group algebras, the relative commutant is injective. So this was just to say that. And it's not known. It's for general algebras, it's It's quite difficult to understand. But at least we know this, and of course this property already distinguishes SL3Z from SL4Z and SL5Z and so on. Because in SL4Z, as we saw, you have this particular copy of SL2Z on the right-left corner, which commandant was centralized there. Yeah, the centralizer in the group contains another copy of SL2Z, so it's impossible. Okay, so now this was for what concerns this property, this kind of solidity. And now let's see what we can say about the regularity of the Galki representation. So I have 20 minutes. Yeah. So we skip all the proof. Maybe. Let's see. So the point is the following. You see, in the case, so take the case of a biexact group, for example, of SL2Z. We saw that from the boundary amenability of this action, we could easily obtain that the Q composition, the left-right representation, is weakly contained in the left regular of the product. This was an easy thing that we proved. So now the general, so from amenability, we obtain this. So the natural question is, okay, suppose that we don't know how to prove amenability, is it possible to translate some dynamical properties, irregularity properties of this particular representation? So the goal is to understand the following. We study the dynamics, this particular dynamic, and we want to deduce regularity of this representation. Okay. So one way so I will tell you about the way to do this, at least for particular dynamical properties. Okay, I have to be precise on what I mean here. So what is really the problem here? So now, take, we want to understand this. So take now, fix what I mean by irregularity property. So take an ideal inside the infinity of gamma times gamma, and we saw that we can construct a C-star algebra of the group out of this ideal, and so I call it phi I, the associated representation of the full group C-star algebra. So we want to understand, for example, if we can retrieve weak containment in this representation from regularity properties. What does it mean that this hold, that this representation, so Q composition lambda times rho, is weakly contained in pi I? What does it mean? It means exactly that for every state on the Galkin algebra, we have that phi composition Q composition lambda times rho is a state on this algebra. It's a state on C star I of gamma times gamma. It's exactly the same point. The continuity with respect to this law. But then we want to understand this. So the idea is to find. So at the end, what we want to do is we want to find actions of gamma times gamma on some spaces with quasi-invariant probability measure. Mu, probability measure mu on X, such that this state, phi, is realized as a vector state associated to the Koopman. This is our goal. So if we can do this, then we I mean, at least we can say that if every Koopman representation constructed in this way is continuous with respect to this C-star topology, then the Calchi representation will inherit the same continuum. So now it's basically an application of Glimm lemma that sorry. So Glimm lemma says the following. For example, one of the versions is that if you take A and B of H separable and also A separable, and you look at a state phi on this algebra and suppose that the state destroys the compact operators. Then there exists a sequence xi n inside H of nor 1 such that phi of A is the limit of the evaluations on these vectors for every A in A. So it's possible to see from this I don't know who observed this the first time, but for example, it's in the PhD thesis by Wills that this actually means that every state, if you take phi on the state on the Calkin algebra, in this case take L2 gamma, then there exist two ingredients. One is a free ultrafilter over the natural number, and another one is a sequence of vectors in L2 of gamma of nor 1, such that the following happen, that the sequence goes to 0 with respect to omega, goes to 0 weakly, and the state phi of A is equal to the limit along omega of evaluations of represented. This is basically what every state in the Calkin algebra is associated to a free ultrafilter on the natural number and a sequence of nor 1 vectors which go to 0 weakly with respect to this ultrafilter.
This is Glimm's lemma. I mean, it just.
Exactly. Yeah. Exactly.
It just. I mean, you have somehow.
It's an easy application.
Somehow replaced taking some subsequences.
It's a trivial application of Glimm lemma. Exactly. Yes. So now we know that every state is like this. So now we start with the phi a state on the Calkin algebra. So phi will be given by this data, psi n and omega. And now the goal is to construct a space and a quasi-invariant measure on this space such that this particular state is viewed as a state restricted to the image of the group algebra is a vector state for this Koopman representation on the group algebra. So first of all, construct the space. Now, I will construct this space, and it's just very abstract, very difficult to understand what is this space. But the point is, as for the by exactness, we want to prove that gamma times gamma on the Stone-Check boundary of gamma is amenable, and then of course we don't study the action there because we don't understand very well what is happening. But what we study is the factors of this. We have some factors that we can understand, and so we study that. And this is the same here. We want to study regularity property on some space that I want to define, regularity properties of Koopman representations, and it's very difficult to understand them, but the point is that we have factor maps, and so we can extend to extension some regularity of the dynamics. So the space I will construct is made in the following way. So take this free, so these are the informations, the sequence and the free ultrafilter. So consider the embedding of L infinity of gamma into the ultra product by this free ultrafilter. So this is just the product of L infinity of gamma over an ideal, where the ideal is the sequence is Fn such that the norm of Fn goes to 0 with respect to the ultrafilter. Okay, this is just a very... So this is the sister algebraic ultraproduct, a very known procedure. I do this is gamma times gamma equivariant. And so by Gelfand duality we have a surjective gamma times... and this is just, the embedding is just the diagonal embedding. I put every function in the constant function, in the constant sequence. So from this we have, by duality, a surjective gamma times gamma equivariant continuous map onto the Stonecheck compactification. And now what I take is just the inverse image under this map of the Stonecheck boundary. So this will be the space that I want to consider. And actually this is just so the continuous functions on this space, call it delta beta omega. The continuous functions on this space are just the ultra product over the ideal generated by C0 gamma. This is just Gelfand duality. Okay, so we have this very strange space. Since the Stonecheck boundary is not complicated enough, we go to an extension. Even more complicated. And now I want to define the measure on this space. So the starting point is we have a sequence psi n that is here. Now I modify a little bit this sequence. So instead of taking psi n, I fix a sequence alpha I inside L1 of gamma, and I do the following. I take the sum of psi n absolute value composition gamma I to the -1, where gamma I is an enumeration of gamma times gamma, and gamma 0 is the identity. So this times alpha I over the norm of this. So this is really just to have equivariant, to have quasi-invariance. So this is my new sequence. I fix this sequence and then it works for every, I mean, it's not important which one I fix. So I take this other sequence, and now what I say is that certainly this gives, it gives a state on the continuous function on the boundary, but also gives a state trivially on this algebra. And so as a state, take the following, let's say L infinity gamma omega to the complex numbers. I send a representative to the limit along omega of Fn psi n tilde psi n tilde. Now what is the point of this state? Is that this measure now, the associated measure, call it mu psi n tilde omega, is gamma times gamma quasi invariant, and is actually supported on this extension of the boundary. Okay, so now we have the space, we have the measure, and we just want to check that the original state is a vector state for this Koopman representation. So we will, I will try to be fast. So the point.
You have 10 minutes.
Yeah, but then
It's not enough.
this is the first step.
Don't worry, you have everything.
So this was by me in Radulescu. So the point is that suppose, so the theorem is the following. Suppose that for every of those measures, for every omega and psi n, the measure mu psi n tilde omega is such that, so call it mu, such that pi mu is pi I continuous for the ideal that I fixed at the beginning. Then the calci rep is pi I continuous. Okay, so the first step in this is a very easy lemma to prove, a characterization of the Kopman representations. If you have, in general, gamma acting on X, you have mu, a probability measure that is gamma quasi-invariant. Then I tell you the following, that pi mu from gamma to the unitaries of L2 of mu is the unique homomorphism such that, one, as Merdad said yesterday, this induces a covariant representation. I think he used the letter rho, so rho mu. Where mu is a covariant pair. So rho is the multiplication representation. And two, for every gamma, pi mu of gamma. So in L2 we have a notion of positive functions. Pi mu of gamma sends the positive part to the positive part. And so why is this true? Well, it's very easy. Proof. So suppose we have another pi, suppose pi from gamma to the unitaries satisfies 1 and 2. Then pick gamma and gamma, and f in C of x. And then we do the following. We take pi of gamma, pi mu of gamma to the -1, e rho mu of f, pi mu of gamma, pi of gamma to the -1. By the covariant condition, this is rho mu of f. So this element, call it V. V is in the commutant, is in rho mu of C of x prime, which is L infinity of mu. So we have an L infinity function. This L infinity function is a unitary. We should send positive elements to positive elements. So it's that empty. Okay. So we have this, and this is just to have a, let's say, an abstract characterization of the Kopman representation, because now we want to exhibit our group homomorphisms and to say that this is the group, the Kopman representation. So how we do this? Well, first of all, we take this particular subset. So take this subset of the ultra product, this linear subspace, and I define it in the following way. Are the sequences such that for every gamma in gamma times gamma there exists a positive constant for which, when I take the absolute value of Fn composition gamma to the -1, this is less or equal than m gamma psi n tilde for every n. So these are functions that are controlled by this psi n tilde. Then it's possible to see, so we take this and then we define V, that is W over psi and tilde. Are the elements obtained in this way. So now it is possible to see that this is, when we go to L2, this is dense, so classes A of B is dense. And now we want to define here our unitary operator. And I say that when I take Fn over psi and tilde, I want to apply V gamma. This will send this to Fn composition gamma to the minus 1 over psi and tilde. So it's easy to see that this preserves classes. It's actually a unitary operator and extends. This is basically what happened. And, just checking. This sends positive elements to positive elements and so on. So this was just to say this. So what we saw is that this psi and tilde realize. Okay. Now the last step is that we want to see that if we are given this data psi n and omega, we can realize the vector state there. But this is very easy because I do the following. I take a particular element. I do like this, P mu of gamma associated to this, psi n over psi n tilde, scalar product with itself. This is the scalar product in this L2 of mu. Now, by definition, this is the limit and that goes to omega of the scalar product of what? Of Cn composition gamma to the minus 1 over psi and tilde. Now here the scalar product is in L2 gamma. So we have psi and tilde, and we have psi n over psi and tilde, psi and tilde. So this erase, and this is actually the limit for n that goes to omega of psi n composition gamma to the minus 1 against psi n. And this is exactly the state we started with when evaluated on the group algebra. And so basically this gives the proof that if we know that all these Koopman representations are continuous with respect to this particular C-star topology on the group, then the Calkin algebra we will inherit the same continuity. Okay, so this was the starting point. I have to, it's finished, the 5 minutes. Okay, so what? Yeah, it's the end. So I will just tell you the strategy now. What is the strategy? The strategy is just to use an analog of the map that we used in the case of SL2Z in order to prove by exactness. That was the map sending a matrix to the projective matrix associated to it, and we saw that the range is RP1 times RP1. Now, if you do something similar here, it's a bit more complicated. What you obtain is that here you have delta beta gamma, gamma is SL3Z. Now here it's we consider a map. Now one has to modify a little bit because one wants to keep track of the Lyapunov coefficients. And so I take the map sending gamma to the projective of gamma, but also the projective of gamma to the minus 1. Okay, this is in the projective 3x3 product of projective 3x3 matrices, and the range has the following property. Either we have rank 1 times rank 1, or we have rank 2 times rank 1, or we have rank 1 times rank 2. Okay, now it's easy to see that here the action is amenable, because it's basically these fibers over a product of quotients by the Borel subgroup. And here, these two actions are basically the same. This has to be, I don't want to be precise on this, but the point is that at the end we want to study the dynamics on this for the left-right action. So here, the important point is so Furstenberg, Margulis, Goldscheid, Abels, they studied a lot of what are called quasi-projective transformations. And this is really, the dynamics here is really related to their study. They understood this proximality behavior, but not for things that go to a point, but maybe to some varieties inside the space. And so what happens here is that if you look at the dynamic here, suppose you have gamma n which goes to infinity in SL3Z, then it's not true that almost every point in general will go to something. But there are some sort of algebraic subvarieties that are defined in the following ways. That, so these are given by matrices. So you have a rank 2 matrix, and so the range should be contained, should contain a given line, and the kernel should be contained in a given plane. And then you have this proximality behavior towards sets of this form. So the point now is to study the inverse image of sets of this form. The beautiful thing is that when you go back, you have these particular sets, you go back, you study. Now you have really to go up to understand this. You study the dynamics on these particular sets. Every Cooper representation there is tempered. This is very, really the most important point. That when you take now a measure on this big space that we have, you decompose in measures supported in inverse images on this and measures which give measure 0 to this. The measures on this always give tempered group representation. And this is really the study of all the structure of SL3Z. And for the other points, what we have is that, so every point, if you have a sequence, every point will go towards a set like this, and this is just, sorry, gamma n, I was wrong. Gamma n, it's a product, gamma n1, gamma n2, so both should go to infinity. This is important. So what we obtain at the end is that for every omega ultrafilter on the natural number, for every pi mu constructed in that way on the probability measures on delta beta omega of gamma, so we decompose pi mu as one supported on inverse images of sets like this, and another one supported which gives 0 mass to them. Then pi 1 is tempered, and pi 2 is pi I continuous. So pi 2 is weakly contained in pi I, where I is the ideal of functions. Of course, it's clear. It's the ideal of functions in L infinity of gamma times gamma, such that f of gamma n at n goes to 0 if gamma n goes to infinity and eta n goes to infinity. So, okay, by what we said before, in particular, the Galkin representation has the same property. And now, is this something interesting for some reason? Well, at least, I don't know if it implies, I still have to understand if it can be upgraded actually, because here maybe there is much more to say. But at least it distinguishes SL3Z from SL5Z. And if you take n greater or equal than 5, this is not possible. And the reason is really that the point is that you have in SL5Z you have an infinite subgroup whose centralizer as property T. Okay. Okay. So yes, this is basically I think. Yeah, sorry. The last rush. Sorry.
Yes. Thank you. time for questions.
So this amenability piece that you have for SL3 and SL2. Okay, so you said something here is not true for SL5, but the previous discussions on SL3, SL2 case for higher ranks, you don't know, but you
For example, no, you mean the solidity stuff, the structure of the von Neumann algebra.
previous stuff.
If you do exactly the same reasoning, you have that for every SLD, Z, for every subgroup, the centralizer is contained in the stabilizer for some parabolic subgroup, not the minimal one. Yeah. So you don't have injectivity, but you have this structure. Yes.
But SL3Z, so it could be a solid still, no?
Yes, this is what I wanted to understand.
Yeah, that's what you wanted to prove.
Yeah, yeah. But what is nice, I think, of this? Okay, there is all the theory, but it's that at the end there is a particular space on which I have to understand the dynamics, and this is it's just really, if I understand more about the dynamics on this, maybe this can be upgraded. I don't know, but it's really a space on which there is some dynamics, and it's a space of quasi-projective transformations. But it's difficult to study, but it's something that one can, if you take time. So for the time being, we only have this type of continuum, but it's possible to, because the difficult part, I mean, the part in which, the inverse images of these sets is the part in which there are all the technical stuff and so on which you obtain temperateness of the representations. And after you have this, you just have to study the dynamics on this set. And it could be that it can be upgraded.
So you still don't have the property AO for, so left, right, so you know the representation is quotient, but you don't know the kernel exactly.
Yeah.
But it somehow, I mean.
And I also don't know if from properties, so an interesting question in my opinion is to understand, the path is clear with the by exactness, AO and solidity. But maybe there is some structure of the von Neumann algebra that is given by this, for example. Papa suggested that maybe you have primeness, but I couldn't prove it. But.
I mean, there is also some notion of weak solidity, which is in between. I mean, there's a bunch of things that it could be.
So, for example, what is one of these?
What separates weak solidity from solidity?
Yes.
I don't remember. But, yeah.
I will have a look. But at least the fact that this distinguishes SL3Z from something SL5Z on, it's at least it's it's a first step. Suggests that maybe it's not just something that we are not talking about something that cannot imply nothing. It's
One quick question. I don't know. Like, so you have a bunch of Koopman representations. Could it happen that they are uniformly bounded?
In general, no, but I think it's possible to restrict something like this. But in general, I don't know, but it's good if they are.
I have seen just examples. You know, you have Koopman representations of hyperbolic groups, and people are interested on like uniform boundedness.
Uniform boundedness?
Sorry, what do you mean by
Yes, you mean the Radon-Nikodym derivative?
Yeah, like in the norms.
But he considers the unitary version of these.
Yeah, that's always, I mean.
So you can
already.
Okay.
So you're asking about the uniform boundedness.
Yes.
The Radon-Nikodym?
Yes.
Yeah.
Yeah, this I don't know, yeah, but...
Yes.
might be that you can only consider those. I don't know.
In these cases, it shouldn't be when you have this proximality, then certainly they blow up the vulnerability.
Yes,
They
yes.
concentrate on the point.
Yes, yes.
Can you measure how fast they blow up?
This is difficult.
Oh, yeah, that's a good question. I mean, in general,
I don't think it's known. I don't know.
no, in general, probably
Yeah.
no.
So I guess it's coffee time. So let's thank Jacopo again.
Finally.
And hopefully there is coffee. Yeah?
What I was asking actually,
They misunderstood.
no, I was asking about something that probably you didn't mention. So, the amenability of SF3 acting
On the boundary of the
Yes.
process. Yes.